Today we will discuss sets, section 2.1. Definition of a set. A set is an unordered collection of objects called elements or members of the set. A set is said to contain elements, and we write A, or lowercase a is an element of capital set A. To denote that A is an element of the set A. The notation, which look like an E with the slanted line, means that A, or lowercase a, is not a member of the set A. It is common for sets to be denoted using an uppercase letters, while lowercase letters are used to denote element of the set. Example of a set. So you have a capital letter A. It's a set that contains elements A, B, C, D, F, and G. This is known as raster method, where you list all the elements and you put them inside a curly brackets, and all the elements will be separated by a comma. So this is one way of expressing a set. Now we will discuss more example of raster method. So we want to list element of a certain set in curly brackets. So for example, you want to express a set of all vowels in English alphabet, and we can write it as follows. V here is a set. V is equal to a set of all vowels A, E, I, O, U, all of them separated by commas, and all of them are within two curly brackets. Example of another set. The set of odd positive integers less than 10 can be expressed as follows. Odd integers less than 10, we call this a set O. So we write O, capital O, which is the numbers 1, 3, 5, 7, 9. These are all the number of odd numbers that are less than 10. Another set, the set of positive integers less than 100 can be expressed by the following. So positive integers, so we call this set N, and then we say the set N consists of 1, 2, 3 dot up to 99. So that means, all the way to 99. These are all the set of positive integers less than 100. Example also, the set of let's call the set of odd positive integers less than 10, and then we call this E. So this is a set of positive integers less than 10. So set of not only positive but also even. So then we have the set E, which consists of 0, 2, 4, 6, 8. Let's talk about set building notation. Set building notation, we use it instead of using the raster method. So set building notation sometimes it's easy to express certain sets using set building notation other than using the raster method. In set building, we characterize the entire element in the set by stating the property or the properties they must have to be the members. Example, consider the set O of all positive integers less than 10. We can write these in set building notation as follows. O, capital O, is the set of all x such that x is an odd positive integer less than 10. Another example. So the set O Q positive of all rational numbers can be written as, right now we want to just consider the rational numbers that are positive. We can just write it in a set building notation as follow. So Q plus is equal to X, where X here is an element of R mean real number, such that X is equal to P over Q for some positive integers P and Q. So here P and Q are both positive. Common sets. We know about common sets of natural numbers n start with 0, 1, 2, 3 all the way to positive infinity. Set of integers which we denote by z, and it includes all the integers positive and negative. Set of positive integers, we denote that by z plus, which only include, it's almost like the natural numbers, except that it doesn't include the 0. Set of real numbers, which are real numbers that we know, and set of positive real numbers, which we denote by r plus, and set of complex numbers, which we denote by c. Interval notation, when a and b are real numbers, with a less than b, we can write a closed interval that consists of a and b. So for closed interval, we usually use like the square bracket, a and b. So that means both the edges are included. And then we can write this using the set building notation. It's a set of all x such that a is less than or equal to x, x is less than or equal to b. For open interval, we use parentheses. So a and b. So that means a and b is the set of all x such that a is less than x is less than b. An open interval is an interval that does not include its nth point, while the closed interval includes its end points. Equal sets. Definition: two sets are equal if and only if they have the same elements. Therefore, A and B are equal if and only if for all x, x is an element of A and x is an element of B, and both B and A are have the same have a property of biconditional statement. So when A is equal to B, if A and B are equal sets. Example of equal sets: the sets 1, 3, 5 and the sets 3, 5, 1. They are equal sets because they have the same element. Also, another example of equal sets is the set that consists of 1, 3, 3, 3, 5, 5, 5, 5, 5, and the set 1, 3, 5. are equal because they have the same elements. Empty sets, it is a special set that has no element, and it is called the empty set or null set, and is denoted by a zero with a slanted line in the middle of it, or an empty curly bracket. Singleton set, a set with one element, is called a singleton set. Venn diagrams. Sets can be represented graphically using Venn diagrams, named after the English mathematician John Venn, who introduced the concept in 1881. In Venn diagrams, the universal set U, which contains all the objects under consideration, is represented by a rectangle. Inside the rectangle, circles or other geometrical shapes are used to represent sets. Sometimes points are used also to indicate the relationship between sets. Here are important concepts that need to be written down about sets. Sets can be element of sets. As you can see here, you have this big set that consists of 3 elements. 2 elements of it are sets. So for instance, you have a set that consists of a set 1, 2, 3 and A, and another set BC, and also a sets that consist of natural numbers, that consist of all integers, and that consist of rational numbers, and that consist of real numbers. The empty set is different from a set containing the empty set. So a null set is not equal to a set that contains a null set. Example: to draw a Venn diagram, draw a Venn diagram that represents V, where V here is the set of vowels in the English alphabet. U is the universal set. So the universal set here contains all the alphabet in English. And then within this universal set, there is another set, which we denote here by a circle. And it is a circle that contains all the vowels letter A, E, I, O, U. Subsets. Definition. The set A is a subset of B if and only if every element of A is also an element of B. We use the notation A is the subset of B to indicate that A is a subset of the set B. We say that A is a subset of B if and only if the quantification for all x is an element of A implies that x is an element of B. Okay? To show that A is a subset of B, you must show that if x belongs to A, then x also belongs to B. Examples: the set of all computer science majors at your school is a subset of all students at your school. The set of integers with the squares less than 100 is not a subset of the set of non-negative integers. The set of rational numbers is a subset of the set of real numbers. Theorem 1. For every set S, empty set is a subset of S. and S is a subset of itself. Proper subsets. Definition. If A is a subset of B, but A not equal to B, then we say A is a proper subset of B, and we denote that by this symbol, which is the same as almost the same as subset symbol, but there is no unequal sign underneath. If A is proper subset of B, that means that every element in X and every element X in that belongs to A also belongs to B. And then we can denote that by this Venn diagram. So here you know that A is fully contained in B. Set cardinality. If there are exactly n distinct elements in a set S, where n is a non-negative integer, we say that S is finite. Otherwise, it is infinite. The cardinality of a finite set A, denoted by, usually we denote it like finding the absolute value of a set, is the number of distinct elements of A. Set cardinality. So an empty set cardinality is 0. The set S, let set S be the letters of English alphabet. Then cardinality of S is 26. The cardinality of the set 1, 2, 3 is 3. The cardinality of 0 slanted line inside a curly bracket is 1. The set of integers is infinite. The cardinality of the set of integers is infinite. Power sets. Definition. The set of all subsets of a set A denoted by P of A is called the power set of A. If A is a set that consists of two elements A and B, then a power set of A is the set null set, and a set that consists of A, and then a set that consists of B, and then a set that consists of A and B. So all these are elements of the power set. If a set has n elements, then the cardinality of the power set is 2 raised to the power of n. The ordered n tuples A1, A2, all the way to An is the ordered collection that has A1 as its first element and A2 as its second element, and so on until An as its last element. Two n tuples are equal if and only if their corresponding elements are equal. Two tuples are called ordered pairs. The ordered pairs A and B and C and D are equal if and only A is equal to C and B is equal to D. Cartesian product. The Cartesian product of two sets A and B, denoted by A times B, is the set of ordered pairs lowercase a and lowercase b, where lowercase a here is an element of capital A, and then lowercase b is an element of a set capital B. So A cross B would be equal to the set that consists of ordered pair A and B, such that A belongs to lowercase a belong to capital A, and then lowercase b belong to capital B. So an example of a Cartesian product. So for instance, if you have a set A that consists of AB and B that consists of element 1, 2, 3, so A cross B is equal to the ordered pairs A1, A and 1, A and 2, A and 3, B and 1, B and 2, and B and 3. As you can see here, element of A, occupy the x-axis place, and then the element of B here occupy the y-axis place in the ordered pairs. So Cartesian product continues. The Cartesian product of the set A1, A2, all the way to AN, denoted by A1 cross A2 cross all the way to cross AN, is the set of ordered n tuples, which is lowercase a1, lowercase a2, all the way to lowercase an, where ai here belongs to the capital A, which is the set A. Okay, so we can actually find Cartesian product not only for two sets but for many sets. So for instance, here you have set A that have element 0 and 1, and set B that have element 1 and 2, and set C that have element 0, 1, 2. So if you want to find the Cartesian product of these, so the Cartesian product of A cross B cross C would be as follows. As you can see in front of you here, element of A would always be in the x-axis, element of B would be in the y-axis, and then element of C would be in the z-axis. So here are the references we use to make this representation.